Ever stared at a physics derivation that takes up a whole whiteboard? Variables pile on top of variables, and by the fourth line of dense algebra, a creeping anxiety sets in. Did I drop a squared term? Did that fraction flip? Finding a mistake in that mess usually feels like searching for a needle in a mathematical haystack. You could plug in sample numbers and test the final result, but that is tedious and prone to its own errors. If you accidentally equate a unit of distance to a unit of acceleration, your numbers might still crunch, but the underlying logic is broken. We need a way to check the structure of the math itself without calculating a single value. That structural check relies on finding a quantity's dimension. In physics, a dimension is the absolute nature of a measurement. Whether you measure a table in meters, inches, or light years, its baseline identity is still length. The dimension doesn't care about the magnitude or the specific measuring stick you used. For the mechanics of the universe, almost everything breaks down into three primary dimensions. We write them in square brackets to separate them from regular variables: m for mass, l for length, and t for time. Think of these three brackets as the base alphabet of physics. These dimension blocks function as algebraic symbols. You can multiply them, divide them, and cancel them out. If you divide length by time, you get L over t, which is the precise dimensional signature of velocity. By treating these dimensions as algebraic units, we strip away the noise of specific numbers. It turns physics from a messy number-crunching exercise into a strict, logical system of checks and balances. This logic gives us a hard rule called the principle of homogeneity of dimensions. It states that you can only add or subtract physical quantities if they share the exact same dimensions. You can't add 5 kilograms to 3 seconds. It makes no physical sense. Try to add a force to a velocity, and the math literally rejects it. The dimensions are incompatible. They physically repel one another in an equation. We can use this principle to audit complex formulas. Take the law of conservation of energy. If kinetic energy is supposed to equal potential energy at a certain point, their dimensional signatures must be identical. Let's run the diagnostic. Look at kinetic energy, 1/2 mv squared. We ignore the fraction because pure numbers have no dimension. Mass is m, velocity is length over time. Square that velocity and you get L squared over t squared. Combine them and kinetic energy reduces to mL squared t negative 2. Now let's check potential energy. Mass times gravity times height. Mass is m, gravity is an acceleration, meaning length over time squared. Height is a length. Multiply those together and you get exactly mL squared t negative 2, a perfect dimensional match. This principle is a ruthless filter. Before you ever plug in the mass of an object or the distance it falls, homogeneity ensures the equation describes a physical reality, not mathematical nonsense. This system also allows us to derive entirely new formulas from scratch. Imagine you need to calculate the time it takes for a simple pendulum to complete one full swing. You don't know the exact equation, but you know the variables involved: the length of the string, the acceleration due to gravity, and the mass of the pendulum bob. We start by setting the time period, t, proportional to those three variables. Since we don't know how they interact yet, we raise each one to an unknown exponent, x for length, y for gravity, and z for mass. Next, we swap those variables out for their base dimensions. The left side of the equation is purely time, t. The right side is a mix of length, time, and mass. By enforcing the rule of homogeneity, we force the exponents on the left to balance the exponents on the right, allowing us to solve for x, y, and z algebraically. Look at the left side of our equation. It is purely time. There is no mass dimension there. To keep the equation balanced, the exponent for mass on the right side must be 0. Since anything to the power of 0 is 1, the mass of the bob effectively vanishes from the calculation. Without running a single physical experiment, the math tells us that a heavy pendulum and a light pendulum of the same length will swing at the exact same rate. We deduced a physical truth just by balancing the dimensions. It is important to know exactly where this tool fails. Dimensional analysis has a specific set of blind spots. It cannot see dimensionless quantities. Pure numbers like pi, or a fraction of 1/2, leave no dimensional footprint. The same goes for the arguments inside logarithmic or trigonometric functions. Take a standard plane angle. Geometrically, it is defined as the ratio of an arc's length to its radius. That is, length divided by length. The dimension cancels out completely. An angle has a unit, the radian, but it has 0 dimensions. If your derivation drops a constant factor, like 2 times pi, dimensional analysis will not catch the error. Recognizing what a diagnostic tool cannot do is a prerequisite for trusting what it can do. Because of those blind spots, a dimensionally correct equation isn't guaranteed to be the exact final answer. It might be missing a crucial numerical constant. But the reverse is an absolute law. If an equation is dimensionally inconsistent, it is unequivocally wrong. There is no gray area. You could build a theoretical model spanning pages of dense calculus, but if, at the very end, the left side evaluates to meters and the right side evaluates to kilograms, the entire model collapses. The math has lost its connection to reality. This is why checking dimensions is the first line of defense in physics. It is a mandatory sanity check. Before you start integrating or crunching massive data sets, you verify the grammar of the equation. Dimensional analysis is the universe's veto power. It is a built-in mechanism to ensure that no matter how abstract our math becomes, it remains firmly tethered to the physical world.